So, welcome back. So, as we're testing these hypotheses, remember the first principle is to always assume that the null hypothesis is true. It's kind of like saying everyone is innocent until proven guilty in a court of law. We're going to assume the null is true, or we treat it as if the null is true, and then we'll determine if the evidence, the sample evidence that we have collected, refutes that or contradicts this assumption. Now, there are two approaches to hypothesis testing. We're only going to be doing the p-value approach. We're not going to be looking at the critical value approach. It's not quite as sophisticated. It's a little simpler. It's more for calculating by hand, and it's not quite as specific. So the good news is that as we're doing these hypothesis tests, and we're going to look at 3 different ones here, all of these tests are things that we have already done. So if you've been wondering up to this point, why in the world are we learning about z-test and t-test and all that kind of stuff, this is why. So none of this part is new. We are going to be jumping into Excel and practicing these in Excel, but you're already very, very familiar with doing it in Excel. So if we're wanting to test the population mean when sigma, the standard deviation, is known, we're going to use our z-score, where mu sub 0 is the hypothesized mean value. And then our x bar, of course, is our sample mean. And we do have to, the mean does have to be normally distributed. So that's, we know, is if the population is normally distributed, or according to the central limit theorem, if the sample size is larger than 30, then we can assume that it is normally distributed. So the p-value approach is the likelihood that a sample mean is at least, I like to think of the p-value as being, it is the probability of making a type 1 error. So remember, a type 1 error is when we reject the null when it was actually true. So what's the probability that we are willing to make that? So typically we'll compute p-values at 1%, 5%, or 10%, which means we're using a significance level of 1%, 5%, or 10%. So the decision rule is to reject the null hypothesis if the p-value is less than that alpha, that our significance level, and then we don't reject the p-value if it is greater than or equal to alpha. Now really you should decide what alpha is before you start testing, so that we are not swayed by what the results show. Now, keep in mind, this is very important. If we're testing that the mean is greater than the null, then we're using a right tail test. If we're testing that the mean is less than the null, we're using a left tail test. And if we're testing that the mean does not equal, then we're using a two-tailed probability. So again, very, very important. That's going to determine how we enter our formulas into Excel. So we want to reject the null if the p-value is less than the alpha, than the significance level. So a left-tailed test, remember, is testing over here this green area that we see in the distribution, the left area. So we're testing for the less than or equal to. A right tail test is testing whether it's in the right side, so that's a greater than or equal to. And then if it's an equal, we're testing for two tails. So we've got a 4-step procedure to use the p-value. First of all, we have to specify our null and alternative hypotheses. We specify the significance level, so is it 1%, 5%, 10%? So what probability are we willing to accept that we've made a type 1 error? We're going to calculate the value of the test statistic and then the p-value, and then we'll state the conclusion and interpret the results. So this is really important. I don't want you to just stop at step 3. It's really important that you are then able to state the conclusion and interpret the results correctly as well. So here we have an example. We have a sample of 30 households that show that the sample mean of back to school spending is $622.85. So we looked at this data in the first video. It is believed that back to school spending is normally distributed with a population standard deviation of 65. And then we have an analyst who's testing to see if back to school spending is significantly different from the mean of 606.40 that the trade group predicted, and that's with a 5% significance level. So we know that the mean is above the 606.40. We're saying, is it above it with a statistically significant? Is it above it enough? Okay. So step one is to state our hypotheses. So the null hypothesis is that the mean is equal to 606.40, and the alternative hypothesis is that the mean does not equal 606.40. Now step two is to define our significance level, which we have already been told was 5% or 0.05. Now, because we can say that this population is normally distributed, we had a sample size of 30, and we do believe that it is normally distributed, we can go ahead and calculate the z-score. So we're very familiar with z-scores by now. We've calculated these a lot. So we're going to take our sample mean of 622.85, subtract it from the test mean of 606.40, and then divide that by the standard deviation divided by the square root of the sample size. And so we get a z-score of 1.39. Now at this point we could flip to the back to the z-table and look up in the z-table 1.39 and figure out what that probability is, or we could jump to Excel and use Excel. So let's jump to Excel. Now before we jump over to Excel, let's take a look at something. Now remember that this is a two-tailed test. So that means whatever value we calculate in Excel, we're going to have to multiply by 2 to calculate the value in both tails. So remember that our p-value test is, for a two-tailed test, we're calculating that the probability that z is greater than 1.39. So in our formula, we're going to use 2 times, because remember it's a two-tailed test, and then we're going to say 1 minus the norm.s.distribution. Now the reason we're doing 1 minus is because otherwise it returns a left-tailed test. So 1 minus is going to give us a right-tailed test, and then we'll multiply that by 2 to give it to us in both tails. So we're going to plug in our z-score, and then the 1 is the second term because it is cumulative. So let's just jump over to Excel and practice this real quick before we move on. So I've got my Chapter 9 Excel spreadsheet open here, but I've just opened a new sheet. I've added a blank new sheet here at the end, and I'm going to go ahead and use this to calculate my p-value. So my p-value, I'm going to go ahead and enter my formulas here. It would be equal to 2 times, because it's a two-tailed test, 1 minus the norm.s.distribution. So this is the standard normal distribution, where my z-score that we just calculated was 1.39. And of course we can calculate our z-score here in Excel as well if we don't want to do that manually, certainly. And then we're going to say 1 because it's cumulative. Oh, I'm missing some parentheses. Let me add my parentheses. All right, so we get a score, a p-value of 0.1646. So that is our p-value. Now let's jump back over to our PowerPoints. So since our p-value of 0.1646 was greater than our significance level of 0.05, we do not reject the null. So therefore we're going to say at 5% significance level, we cannot conclude that average back to school spending significantly differs from the 606.40 that we were testing for. Okay. So we can also use confidence intervals to use hypothesis testing. I'm not really going to go over that. We do know how to calculate confidence intervals. We've done that before. So just know that you can use a confidence interval. So your decision rule is looking at whether or not your the population mean falls within the confidence interval. And we will reject it if it does not, and we won't reject it if it does. So just looking at an example here, we could calculate our confidence intervals, which again, we're very familiar with doing by now. We're going to take our sample mean, our x bar, plus or minus our z-score, multiplied by alpha, our significance level, divided by the square root of n. And then we'll see if the mean falls within that confidence interval, then we do not reject. And if it does not, then we will not reject. So again, this is just another way to do it if you didn't want to calculate a p-score or p-value. So again, looking at just continuing our example with our back to school spending, if we calculate our confidence interval, remember we have to divide it by 2 because it's a two-tailed test. So if we calculate our confidence interval, we get a confidence interval of 599.59 as our lower limit and 646.11 as our upper limit. So since our sample mean fell within that range, we cannot reject the hypothesis. So we come to the same conclusion we did using the p-value. Just the p-value is a little easier to calculate than this confidence interval. Now, if we don't know what the standard deviation is, then we can still use a t-test with n minus 1 degrees of freedom to calculate our term that we need to calculate our p-value. Now again, remember this is only valid if our sample mean follows a normal distribution. So again, we've calculated the t-test with the degrees of freedom. We're going to use the sample mean minus the null mean in the numerator, and then the sample standard deviation divided by the square root of the sample size in the denominator. So we've done this before. This is not new to us. We're just now looking at it from a p-value perspective. So now we're going to jump back to the introductory case. I hope you read through it. We have there's a study that was done that said in 1961, students studied on average 24 hours per week. A dean of a college in California wonders if students are studying significantly less than that now. So she randomly samples 35 students and asks them their average study time, and gets a sample mean of 16.3714 hours and a sample standard deviation of 7.2155 hours. So to go ahead and test the hypothesis that students now are studying less than they did before, we'll compute our hypotheses. We'll calculate the value of the t-test here. We'll find the p-value, and then using a 5% significance level, we'll come to our conclusion. So let's state our hypothesis. The null hypothesis is that students are studying the same amount or more, so at least 24 hours. And the alternative hypothesis is that students are studying less than 24 hours now. So our significance level has already been stated at 5%. Now, since n is greater than 30, it was 35. Remember, we can assume that the sample is normally distributed. Goodness. So we can go ahead and calculate our t-statistic, and we've done this before. We can calculate this in Excel, or we can calculate it just here by hand. But we're going to calculate our x bar minus our test statistic of 24 divided by the sample standard deviation divided by the square root of the sample size. And so we get negative 6.255. And now we can jump over and calculate our p-value, where we're testing that the mean is less than 24. Now this is a left-tailed test. So one thing very important to keep in mind, if we're looking at the alternative hypothesis as being less than, it's a left-tailed test. If it's greater than, it's a right-tailed test. So that changes what test we're going to run here. So this is important. And so for a left-tailed test, remember we have to subtract because the test by default, in fact, it's called a right-tailed test. We're going to use a t-distribution looking at a right-tailed test. So to calculate the left tail, we have to subtract from 1. So let's jump over to Excel now, and we're going to go back into our Chapter 9 worksheet, and we're going to look at the study hours worksheet. All right, so again, I'm in my Chapter 9 workbook that's posted there for you in Blackboard. I've got the study hours worksheet pulled up, and I want to just go ahead and start from the beginning here. So first of all, let's go ahead and calculate the average of the sample. Now, I know that we know how to calculate the average, but just to be complete, let's go ahead and do it. So our data goes from A2 all the way through A36 because, of course, we have 35 items in our sample. So to calculate the average, I'm going to say the average of A2 through A36, and that gives us the average that we were given before of 16.37143. I can also go ahead and calculate the standard deviation. Remember, we've done this before too. So we're going to use standard deviation. Don't forget to do the .s because that's for the sample. And again, I can say A2 through A36. And then we get our standard deviation of 7.215529. Now, I'm just going to go ahead and type this in here. N is 35, just so that we have that to remember. So now I can calculate my t-test with 34 degrees of freedom. Remember, the degrees of freedom are always 1 minus the sample size, so 35 minus 1. So my t-test here, the formula, remember, is we got to remember to use our parentheses. It's going to be the sample average minus the null mean, which was 24. That's what we're testing, divided by, let me open some more parentheses, the standard deviation divided by the square root of the sample size, which I've put there in D4, and then close all my parentheses. And so there I get my t-value of a negative 6.25474. Goodness. So now I can calculate my p-value by saying, again, remember the p-value, the t-test is looking up the right tail, so I'm going to say 1 minus t dot distribution. Now there's the two-tailed t-test. Here's the right tail t-test. So this is the one tail. X here is my t-value here in D5. Degrees of freedom, remember, is 1 minus n, so I can type in 34, or you could put the formula in if you wanted to. And then I press enter. Now, notice I get 2.01 blah, 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 but it's written in scientific notation. It's to e to the negative 7, which means you've got to move that decimal place 7 places to the left. You've got 7 zeros before we get to that 2. So what this means is this is an exceptionally small number. Exceptionally small number. So it is most definitely less than 0.05. It's exceptionally small. In fact, if we were to look it up in the table, we would see that it's less than 0.005, which we know it is because it's really less than 0.000000. I forgot how many zeros there were, but 7 there, 2, right? So it's exceptionally small. So then we definitely can reject the null hypothesis. So let's go back to our PowerPoints here. And so since the p-value is less than 0.05, way less, we can reject the null hypothesis. So we can conclude with 5% significance level that the average study time at the university is less than 24 hours per week. All right, so then one last test that let's look at. Let's look at the test for the population proportion. So here again, we're using a z-test, but we've done these before again, but here for our population proportion is the proportion of the sample minus the proportion of the null hypothesis, where the proportion of the sample is x divided by n, where x is the number of successes that we had divided by n. And then the hypothesized value of the proportion is P null or P0. Now again, we can only use this formula if it is approximately normally distributed, and we can test that by saying if NP is greater than or equal to 5 and N times 1 minus P is also greater than or equal to 5, we can assume that the sample is normally, or the population is normally distributed. All right, so here we're told that a popular magazine asserts that fewer than 40% of households have actually changed their lifestyles because of environmental concerns. They recently surveyed 180 households, and they found that 67 have made actual lifestyle changes due to environmental concerns, but only 67 out of 180. So first of all, we're going to state our hypothesis. Our null hypothesis is that the probability is greater than or equal to 0.4, and therefore the alternative is that it is less than 0.4 or 40%. And we are again setting our significance level at 0.05. Now, we can go ahead and test NP. So is equal to 67 times 0.4, which is greater than 5, and N times 1 minus P is greater than 5 also. So we can assume that this is normally distributed. So we can compute our test statistic. Our P bar is the number of successes, 67, divided by 180. So we get a P bar value here of 0.3722. And again, we can easily do this in Excel if we wanted to. And so to plug this in and calculate our z-score, and again, we can do this in Excel just like we've done before, but when we calculate this in Excel, we get a z-score of a negative 0.76. So now I can compute the p-value. Now here I'm looking for a left-tailed test. So I'm going to use the norm.s.distribution. Now this is calculating the left-tailed test. So if I were wanting a right-tailed test, I would say 1 minus this. Remember, it's the t-test that calculates the right tail. The standard distribution calculates the left tail. So that's a little confusing. You may want to make yourself a note of that. So let's jump over here to Excel. So here I'm back in that blank worksheet that I was working in before. Here we have our p-value from earlier. So let's just delete that there. And we'll go in and calculate our new p-value, where we're going to say the standard normal distribution, so norm.s.distribution, where my z-score that I just calculated was a negative 0.76. Remember, it's in the left tail, so it's always negative if it's in the left tail. And it is cumulative. And so here I get a p-value of 0.22. So since that is greater than 0.05, we cannot reject the null hypothesis. So let's jump back to our PowerPoints. So since, again, that p-value of 0.22 was greater than 0.05, we cannot reject the null hypothesis. So therefore, we cannot conclude that fewer than 40% of households have actually changed their lifestyles because of environmental concerns. So for this chapter, you have homework and you have an Excel simulation. Don't forget to do both for this chapter. And then we'll pick back up in chapter 10, where we continue this hypothesis testing, but now we're going to be looking at comparisons involving more than one mean.